Welcome to this presentation. In it, we're going to cover the Android's operating system's architecture and how it has evolved throughout the years. This presentation is split into two parts. In part one, or this part, we're going to get a general overview of the architecture itself and perhaps a little more detail on how it works, and also get an answer to the question of why it came to be this way. In part two, we're going to look at its evolution through time, since its inception up until the present day and even going forward. We're also going to get an answer to the question of what these four things have in common. Dalvik, a small fishing village in Iceland, How, a robot from a famous sci-fi movie classic, art, and cupcakes. Without further ado, let's begin. We'll start out with a brief overview of the Android operating system. I'm not going to bore you to death with all the history of Android or anything like that. However, knowing a few key things about it would give us a better perspective into the operating system itself. So it started out in 2003, actually as an operating system aimed to control digital cameras. Soon enough, the founders at Android, however, realized that that market wouldn't be very big, so that they shifted their priorities from developing Android OS as an operating system for cameras to a operating system for mobile devices. In 2005, Google realized that there would be a very big need for a mobile operating system, and so they acquired Android. Fast forward to 2007, which is when Android was announced to the public, and 2008, the following year, when the first hardware device running Android was released. However, at that point in time, their biggest competitor, Apple, had already hit the market with their own mobile operating system. They had already released the first iPhone running iOS. That marked the beginning of the endless war between Android or iOS and Android OS. Of course, that's not the last you would hear about Android because they have a few tricks up their sleeve, but we'll come back to that a little bit later. We also have to keep in mind that Android or the Android operating system is not limited to mobile devices. It's an operating system that supports tablets, TVs, wearable devices such as smartwatches. Most recently, it has been gaining attention into the automotive industry, controlling electronic vehicles and navigating them. And my personal favorite, running Android OS on a mirror in your home. Not sure why you'd want to do something like that because the whole point of a mirror for me is to look at my own reflection, but I guess it's very cool. So let's jump up to the next section in the presentation. Android's architecture. On the right side, we have a graph representing the Android architecture. First of all, this graph is a little bit outdated, so it's not exactly accurate. We'll take a look at a more modern version, get to part two of this presentation. However, it will still serve the purposes of going through the Android architectural stack. And that's right, Android uses an architectural stack, or in other words, uses a layered architecture. It has different layers. For example, the first one being the Linux kernel, the second one being the hardware abstraction layer, and then you have your native libraries and your Android runtime. I know this sounds confusing, but we'll look into each different layer in just a minute. And then you have your application frameworks and your applications at the top. This sounds really complicated. And first, what I would want to do is I would want to briefly discuss what a layered architecture actually is before we begin into diving into each different layer. So a layered architecture is a type of design pattern, not only common in software development, but common also in the physical world. For example, if you think about the pyramids, they are a type of layered architecture. You know, they were made by stacking rocks on top of each other, layer by layer by layer. And this gives you certain benefits when you're working that way. For example, some of the benefits in approaching that problem is it helps you simplify things. So, which is easier, stacking rocks one on top of the other, or perhaps the alternative approach, taking a massive rock or a mountain or something and trying to carve out a pyramid out of it? I would argue that stacking one little rock at a time would be much easier than actually carving massive rocks. Not only that, but it supports change and it can be extended. For example, if you wanted to um, extend your pyramid or swap out a rock that perhaps you don't like, it's much easier to take out one of the rocks and put one on top. It's not so easy if you were carving it outside of a mountain or something. You wouldn't be able to stack more layers on top because you're not permitted to do that. You're not working under a layered architecture. And so these same benefits can be translated into software development as well. There's also a third major benefit using this approach, and that is it the layers can serve as abstractions. And you can think about using electricity at home or turning on the light at home. When you turn on the light in your room, you just need to press the light switch and the light turns on. So you press your switch and let there be light. Very simple. You don't have to worry about how electricity works. You don't have to worry about how electricity comes to your building or how it's produced in the power plant or anything like that. Don't need to worry about the switch or the wires. You just need to know how to press the switch and how to operate it. And the same concepts apply to software development as well. If you think about playing an application such as Angry Birds on your Android device, the only thing you need to worry about is playing the game and having fun. You don't need to understand how the application was developed, how your mobile phone turns on its screen, or how the battery manages its resources, or things like that. All those things are abstracted by the different layers in the Android stack. So it serves as an abstraction. In the next section, we're going to look at the Linux kernel. The Linux kernel in the Android operating system. That's the bottom layer in the architectural stack in Android. First of all, we need to understand what a kernel is in order to talk about this layer. The thing to realize about kernels is that there is a kernel inside of every modern day operating system. Would that be Windows, Apple, or different distributions of Linux? They all have a kernel inside of them, and Android is no different. A kernel is a vital part of the operating system and it handles different things. For example, it shields the upper layers of the software stack from hardware variation. Think about it this way: your phone has a camera inside of it, or a processor, or some other types of hardware inside. In order for you to communicate and send instructions to the camera or your processor, you have to translate those instructions. And you might have an application that is made to take photos on your camera. That's great. But what will happen if you have to send those instructions to a different phone running the same operating system? That different phone might have a different camera at the back. And suddenly, if you send those same instructions to the different phone with a different camera, you wouldn't be able to take your picture anymore. Your instructions wouldn't function because the new camera would expect slightly different instructions. And the same goes for the other pieces of hardware. And hardware is constantly changing in mobile phones. You know how many new mobile devices come out each year and how much mobile devices there are out there already. It's a huge variation. So the kernel handles those tasks for you and it handles them by using different drivers. You can see here in the layer, we have a display driver which handles all the communication with the display, no matter what kind of display it is. Next year this might be a different display. When you send the instructions to it, it makes sure that it still does its job. It has camera drivers, USB drivers, things like that. Those drivers handle this task for you, and you don't have to worry about it. It also mediates access and sharing of hardware resources. So what does that mean? Well, if we take our example again with our phone and we focus on the back of our camera, we only have one camera here at the back. And we might have several different processes or services or applications that want to do something with that camera at the same time. Well, the kernel kind of handles which one of those would have access at which point in time and manages the resources not only in the processor but in the different types of hardware as well. So that's another key point that the kernel just does for you. Another thing is it handles power management. So when your phone should go to sleep, how it should wake up, things like that. That's also a vital part of the kernel. And naturally, you might have a question when you hear that Android uses the Linux kernel. If Android is an operating system and every operating system has its own kernel, why is it using the Linux kernel, a kernel that already exists? Why didn't they develop their own kernel for their own operating system? And there are several reasons why they took that approach. The first one is they didn't want to reinvent the wheel. Building out your custom kernel is a monumental task. And when they were building out Android, they were already lagging behind Apple and iOS. So they had to act faster. If they had to build their own kernel, it might have taken them years to just develop that alone. But there are other also important reasons. For example, the Linux kernel is open source, meaning that they could utilize it for free, modify it, and do pretty much almost whatever they wanted with it without paying any licensing fees. Another reason is it is secure and tested over time. So at the point in time when Android was first developed, the Linux kernel was already 10 plus years old. And in that amount of time, it was attacked several different ways and there were security patches for it. So it was already a very secure environment and it stood the test of time. Another reason is it had, and it still has, a huge community and support backing it up. So you could see how it's future proofed in that way. And up until now, we've been talking about how Android uses the Linux kernel, but that's not exactly correct. It actually uses a modified variant of the Linux kernel that is more suited for the Android operating system and mobile devices in general. So, although it would be great to just be able to take the Linux kernel and put it inside of Android, I'm sure the developers would have preferred that. It wouldn't have worked as well. And so they've added certain modifications and turned on features that the Linux kernel might have originally had, but they've expanded upon them. And these modifications are usually referred to as Androidisms, and it's what makes the Linux kernel inside of Android unique. So some of those Androidisms is, for example, the power management department inside of this kernel implementation. It's pretty different than your typical power management in the normal Linux kernel. The normal Linux kernel was originally developed for desktop devices, and power management between a desktop device and a mobile phone is vastly different. For example, if I take my phone here, you can see its screen lights up, and it's going to stay awake for a few seconds, but then it's going to start dimming and eventually after a few more seconds it shuts off completely. If you compare that to a desktop device or even a laptop, if you leave it like that on your table, it's going to maybe put its display to sleep after 15, 20 minutes. And that's because mobile devices primarily run on battery, whereas even laptops, they're most of the time charging or connected to a socket. And so power management for mobile devices has to be much more aggressive. It needs to shut off your screen as soon as possible, for example. And so it was modified in the Linux kernel to account for that. There's also other drivers that are not in this picture, but if you think about a modern phone, it might have different pieces of hardware inside of it that a typical laptop or a desktop computer doesn't. So it has different sensors for tracking motion, infrared sensors or hardware pieces for payments, contactless payments, and things like that. The Linux kernel originally it didn't have to deal with these pieces of hardware. So it didn't have drivers for them and it didn't have to communicate with them. And so this modification allows you to add these drivers and you can communicate with those devices. Another thing the Linux kernel, which is implemented in Android OS, does differently is the IPC driver. And the IPC driver in Android is called Binder, which stands for Inter-Process Communication Driver. We're not going to dive deep into what it exactly does, but basically it handles the communication between different processes inside of the processor. So if you have one application and another application, usually they run in two separate processes, and they can't communicate with each other. But sometimes they need to communicate with each other. And Android handles that communication in a very interesting way with this driver. And again, it's made much more efficient. So those are some of the key differences inside of the Linux kernel that is implemented in Android OS. It's built on top of the regular Linux kernel, but there are quite a few modifications made to it, and that makes up the bottom layer of the Android architectural stack. And from there on, there's more and more abstractions, which we're going to cover in the next sections. The next section in the Android architecture stack is a combination of layers. It's called the middleware. The middleware consists of several different layers, which we'll dissect into more detail in the upcoming slides. At the bottom is the hardware abstraction layer. Then we have some native libraries, the Android runtime, and on top is the application framework. So the middleware resides on top of the operating system's kernel, but below the applications. And the application layer, the topmost layer, are the applications on your phone as a user you actually interact with and use on a daily basis. So everything in between here is the middle layer. Also, one of the main points of the middleware is that it leverages advances in hardware and software technologies. So for example, here we have some libraries which are already developed and a lot of them are open source. These are different technologies that allow developers to kind of not reinvent the wheel once more and simply implement it inside of Android, which gives a lot of power to the system. Another thing it does is it shields the Android stack from low-level hardware details. So it must be a nightmare for a developer if he had to program everything on the kernel level. It would be a real nightmare because things aren't as abstracted and it's very, very complicated stuff. In this layer, where a lot of the development actually happens, the developers are using daily programming languages like C++ or Java even, which are very abstracted and much easier to program with. So that's in short what the middleware is supposed to do. In the next section, we're going to overview the first part of the middle layer. The hardware abstraction layer, or if you're more familiar with a sci-fi movie by Stanley Kubrick called 2001: A Space Odyssey, it stands for HOW in short. You might be scared, especially with all these Androids and now HOW, things like that. You shouldn't. Let's look at what this layer actually does. So the main job of the hardware abstraction layer is to decouple the software from the hardware so that apps don't break when the hardware changes, for example. And you might be asking yourself at this point, isn't that the kernel's job? I thought the whole point of the kernel is to do exactly that, to have, let's say, a camera driver and handle when the camera changes so that your app still works even though your camera has changed. And the answer to that is yes and no. So yes, that is the Linux kernel's job, but also it can't do everything. And that's why you have this hardware abstraction layer at the top. For example, the Linux kernel doesn't know all the stuff it has to expose that Android wants to expose. Like, for example, having a radio in your mobile phone or a motion sensor or GPS even. A lot of desktop devices don't have such hardware components. And so they're implemented in an abstraction layer on top so that they're handled that way. Kind of like the drivers in the kernel, but in the hardware abstraction layer instead. Also, typical devices like cameras, yes, they have a camera drive inside of the Linux kernel, but if you think about it, the camera on your mobile phone is used completely differently than the camera, let's say, on your laptop or on your desktop device. They're so different that there's a need for kind of like an additional driver or an additional component that would perhaps send different set of instructions to that hardware device, in this case, the camera. And so the Linux kernel by default, it cannot do that. So that's why you also have the hardware abstraction layer on top that also deals directly with some of the hardware like the camera. However, probably the real reason why you have this hardware abstraction layer at the top is not a technical reason per se, and more to do with licensing. So the Linux kernel is open sourced, and that's a double-edged sword for the device manufacturers. On the one side, they can copy the code and they can reuse it and they don't have to pay a licensing fee, which is great. That's why the Linux kernel was used in Android. However, on the other side, any modification you make to the kernel needs to be made public. And so if you're a device manufacturer like Google or Samsung or someone else, and you develop a proprietary camera driver, which boosts the quality of the photos you make with your phone, that's a competitive advantage. And you don't want to share that competitive advantage with everyone. So if you include that driver inside of the Linux kernel, you would have to share it with everyone. However, if you add it to the hardware abstraction layer, you don't necessarily have to share it with anyone unless you want to. So it's mostly to do with having a different license. That's another thing to keep in mind here. The good news is that unless you're a device manufacturer, you hardly interact with this layer. So again, device manufacturers like Samsung or Google or let's say Huawei or other types of device manufacturers, they might want to do some work in this layer. But if you're a regular developer or someone that just uses your phones and applications, you would probably never have to access this layer. The Android runtime environment and the core libraries inside of Android. Let's get started. So we're going to begin with the libraries, or more commonly known as the native libraries. So these are a set of libraries written in C and C++ that are imported inside of Android. A lot of them are from open source projects, and the reason for that is because they didn't want to reinvent the wheel. So for example, we might have a library called the Surface Manager. This would basically handle all of the user interactions with the display or the surface of the device. We have a framework called the media framework. So this would handle different types of encodings for video files, for example, or SQLite. This is something that handles how the data is stored on the device, maybe data you enter inside of your applications. So a lot of these solutions come from other projects, which are then imported inside of Android. And again, they're imported for the same reason, uh, just how the Linux kernel was originally imported. They don't want to reinvent the wheel. There's already a solution that does what they're looking for in a very good way, and they're already open source, so why not just use that instead? Of course, some of these are not actually from open source projects. Some of them are maybe based on open source project or even entirely developed by the Android team where they couldn't find another solution. So they had to develop them from themselves. But a lot of the core power of the Android operating systems comes from here and these set of different libraries that give developers the opportunity to do very complicated stuff. Um, the next part of this layer is the Android runtime. So the Android runtime allows the execution of Java-based applications and Android's own system components. And this might sound a little bit confusing because we haven't talked about Java-based applications or anything like that. These are from the top layers here, the application framework and the applications. So most of the applications in Android are actually written in a language called Java. And in order to be able to actually run those applications on a system, you need a runtime environment. And we'll talk about why that is and how Android implements that runtime environment. But for now, all you need to know is that most of the applications are Java based. And so there is a prerequisite needed for them to be able to be run on the device. It also gives access to Java core libraries and Android class libraries. And these libraries, again, help the developers to make whatever they want and they're standard. So a lot of the Java core libraries, developers have known about them and used them before even Android was developed. So they're familiar with them as well. It also provides both of the both the Java applications and the Android components to interact with some of the other layers here at the bottom. So through this runtime environment, developers can then communicate with the native libraries or even the hardware abstraction layer or even the kernel in certain cases. So it allows them to hook into these kind of bottom layers through this runtime environment. And now let's look at the quick overview of why perhaps Android uses Java applications and why they need a runtime environment to begin with, and perhaps how that runtime environment is a little bit different than regular runtime environments. So in order to understand all of that, we need to understand how Java is different than traditional languages. We already know that most of the applications in Android are Java based. So Java is what we call an interpreted language, and compared to more traditional languages like C and C++, it functions in a different way. Every type of human readable programming language cannot be directly fed to the underlying hardware, let's say the processor. So if you have some code written here on the right side and you try to pass it to a processor, it won't understand what you're trying to do or what you're telling the processor to do because it doesn't understand human readable code like C or C++ or Java. So what needs to happen in a typical traditional programming language like C or C++, you need to write your code and then you have to run it through a compiler. And basically what the compiler does is it transforms this code or translates it or compiles it to machine language or type of code that your processor or your underlying hardware would actually understand. And then when you have that executable file that has the translated machine code, you can run it on your processor or on your hardware or on your device. The benefit of this is that once you compile your code, once you run it through the compiler, you don't have to run it again. So although it might be an intensive task to compile it once, you only have to do it once. And then you have, let's say, a file that you can run on your device again and again and again. You don't have to wait for it to compile again and again. The drawback of these more traditional languages is that this machine language file that was compiled once might not work, and there's a very high chance that it won't work on a different type of hardware, or at the very least on a different type of operating system. So if you think about Mac OS and Windows, you have two different operating systems, and you need to have, if you want to install the same application on these two different operating systems, you'd need to have one installation file for Mac OS and another one for Windows because they behave differently. Okay, and so you'd need to compile your program twice, once for Windows, once for Mac OS. And sometimes you need to compile it multiple times for not only the different operating systems, but for the different hardware components. So that's kind of the drawback here. It's fast because once it's compiled, you don't have to compile it again, but it's not as flexible because you might have to compile it multiple times. Now, if we compare that to Java, the way Java handles this is you have your regular code you've written, and then you feed it into a Java compiler. And the Java compiler, instead of outputting a file that could be understood directly from the processor or your computer or your mobile phone's hardware, it outputs a Java file. And now this Java file, you can take it and you can put it on different devices, mobile phones, different operating systems like Mac OS, Windows, and things like that. You can put it in there and you can run it directly in there. So you don't have to compile it 50 times and you need only one file to be able to run it on the different devices and operating systems. And then once you run it on a device, it's actually going to be compiled in real time. So once you, let's say, double click that file, it's going to enter a Java virtual machine, which almost any modern day kind of computer, mobile phone, or anything like that has one of those. And so it's going to compile it in real time and output it to machine code so that your processor understands it. Now, the benefit of this is that obviously um, you don't have to have different files and you don't have to compile it for all the different hardware or operating systems. The drawback of this is that it's not as efficient because every time you try to execute that program, it has to first be compiled in this virtual environment, this Java virtual machine that does that and translates it to machine code. So in short, those are the differences. And so the Android developer team, they decided, let's use Java. And one of the reasons is exactly this: is it's very flexible. So they don't need to do anything extra to make it work on the various different devices uh, in terms of hardware, or even when updating the operating system. This allows them for it to work on all these different domains. Another key feature of Java is it has extra features built on top of it. And it's a little bit more abstracted than C and C++. Generally, it's easier to program in Java than those languages. And also, it has a few features that those languages do not have. Also, it was popular at that time when Android was being developed, and it's still widely popular. So developers were already familiar with it. And as we mentioned before, it's not as efficient as other languages. So now that we know that, Android has its own type of Java virtual machine implemented inside of it, and it's called Dalvik. And in the beginning of the presentation, we mentioned it gets its name from a small fishing village in Iceland. So this Android runtime environment, it has the Dalvik virtual machine in it, which is a type of Java virtual machine. It basically takes that Java code usually and then transforms it into machine code. It's a little bit different, but it's kind of based on the Java virtual machines. However, it had to be changed and modified than typical Java virtual machines because it has to run on mobile devices. Typical Java virtual machines, they're not efficient enough and they're not used to working on these lower memory devices. So it had to be optimized. And also, it does work a little bit differently at its core, but it serves the same purpose. And the important part about this Dalvik virtual machine is that every application starts out its own instance of the Dalvik virtual machine. So it creates a sandbox for all of the different applications, which aids security as well. Um, so to recap about the Android runtime environment, here are the things it does. So it manages the execution environment that runs Java-based applications. We already talked about that. It provides Android apps, portability, and consistency across various hardware, like a Java virtual machine. It includes many of the core Java libraries developers use. So these core libraries here that are typically part of the Java programming language, they're also included in the runtime environment. So developers can make use of them, and they already know how to do that. So it's not no extra learning on their part. It also includes some of the core Android libraries. So these might be libraries that the Android team developed that other developers can use to develop their own applications. They're also stored in here, and the developers can use those as well. And it provides both the Android components and custom application access to the bottom layers here, the hardware abstraction layer, the Linux kernel, and even the native libraries that are written in C and C++. So in short, that's what the Android runtime environment does. The application framework layer. What does this layer actually do? Well, in short, it contains system services that provide applications with the capabilities they need to do their work. And it does that by providing different services. Typically, these services would start when the phone starts, and they would run in the background and do their little thing without you even knowing. So, for example, the window manager, it manages all of the windows on mobile phone, for example. All of the different applications run in different windows. This is what manages them. Package manager, for example, manages how your applications are packed. It packs them into files called .apk and stores them. The activity manager is vital. It is responsible for launching different applications, terminating applications, basically tracking their activities, things like that. It's very complicated and intricate. And also another part of this layer is exposes hardware and Linux uh, kernel capabilities to the applications themselves. So if you're a developer and you're writing code, this is what allows you to write your code, let's say in Java, and to directly interact with some of the hardware or the Linux kernel drivers directly in Java instead of writing it in more low-level layers, which is much more complicated. So it's also again serves as an abstraction, and it makes the developer's job much easier. As we mentioned, a lot of these services that allow all of these things, they run continuously during system operation. The majority of development is done through the services in this layer. Uh, so the majority of development is done in Java, but of course some of it C and C++ with lower layers as well. The applications layer. Finally, we're at the top of the stack. This final layer. This layer hosts all of the applications you're probably already familiar with. The majority of the applications are written in Java, and there are some that also utilize C and C++. Mostly high resource intensive applications like games, they have to tap into some of the lower libraries directly code into C and C++ for performance benefits. Most recently, Android has been pushing a programming language called Kotlin as well. We'll talk about that, the evolution of the architecture in part 2 of this presentation as well. So some of the newer applications might be developed in language as well. We also make two distinctions between applications. We divide them into user application and system applications. The difference here is that user applications are installed by the user, system applications come pre-installed on the device, and you cannot remove them, whereas user applications, of course, you can. Also, system applications typically have certain permissions automatically granted to them, whereas user permissions, um, you, the user, grant the permission to applications. And that was it regarding the architectural stack of Android, or at least how it actually began. Later on in part 2, we're going to be looking at how it has evolved through the years. So there are quite a few changes to cover. We finally made it to the second part, where we will be taking a closer look at the architectural evolution throughout the years of the Android operating system. Before we begin looking at the actual evolution, I wanted to circle back to the image we were reviewing. As mentioned before, this is a slightly outdated representation of the Android stack. If I hover over here, we can see the new graphical image and new representation from Google of the new stack. So a couple of things have changed here. If we look at the Linux kernel layer, we can see there's another thing in there that's called the secure element. Now we'll review what that exactly is in the future slides. However, we should know that this is in there now. Another thing that has been changed is under the Android runtime environment, we can see that the Dalvik virtual machine is there. However, in the new architecture, we can see that it's replaced by something called an Android runtime. We'll cover what that is as well. There are some other changes visible in here that are not as significant, but we'll try to review most of them. So without further ado, let's get started. Okay, so this is the Android timeline. As we remember from before, Android was released in 2008, and we were reviewing what the original architecture did in the first part of this presentation. In 2009, the first update to Android was released, and this version was Android 1.5, but it also had the name Cupcake. And so starting with this version officially, every Android released had a name was named after a dessert or a confectionery item. So all of the future releases also had these extra names added to them, which is interesting. Moving on to 2009, we saw the release of Android 1.6 or Donut, and this was just an incremental update, nothing major changed in the architecture. And the same thing can be said for Android 2.0, or also named Eclair. It was also an incremental update where no significant changes to the architecture could be observed. Following along in 2010, we saw the release of Android 2.2 or Froyo. Now this release actually had some changes. The first being a change to the Dalvik virtual machine. So the change brought just-in-time compilation, whereas the Dalvik virtual machine originally had ahead-of-time compilation. Now these are complex terms, but essentially it gave a performance boost and faster load times because it changed the way how apps were being compiled in the virtual environment. It also added something called the Android Secure Containers. And what the Android Secure Containers are, it's a way to prevent applications from being modified or corrupted by other programs. So it's a security feature. In other words, it prevents programs from being tampered with. Another kind of cool change was that now you could install applications on external hard drives like SD cards. And who remembers those, right? Um, Back in the days, you could actually add SD cards to your phone. A lot of the providers nowadays have taken out that functionality, unfortunately. Moving along, after Froyo, we got Gingerbread. And we can see that there aren't many notes here for Gingerbread, other than the fact that this is the first version to officially support some kind of an NFC technology. And for those of you that don't know, the NFC technology is that kind of wireless payment used in credit cards, or obviously you have it in modern day smartphones as well. We can pay with it. So this was the first version to see a support for such a device, for such a communication method. It's also the first version to gain widespread adoption. So the previous versions, they weren't as popular as this one. This one really hit it out. The ironic thing is it's a version that's notorious for being one of the most vulnerable Android versions as well. So even though it gained a lot of popularity, it was very vulnerable. After that, in 2011, we got Android 3.0 or Honeycomb. Now, Android Honeycomb is the only Android version whose source code was not made open. As we talked about before, Android as a platform is open source and you can see its source code. However, with Honeycomb, Google decided not to release all of the source code aside from selected portions. This made vendors very wary of the ecosystem as a whole. And though Android is free, Google still controls the system, and its licensing can change at any point in the future. So this was kind of a reminder for everyone. Apart from that, Honeycomb was special because it was a tablet-only release. So it was mainly targeted at bigger screen devices such as tablets. Nonetheless, some vendors still try to use it on phones, sort of hack it so that they can use it on mobile phones. In terms of features that it introduced, it actually enabled multi-core support for Android. So up until this point, Android would not be able to function with multi-core processors. Obviously, this is a huge thing, and moving forward, every Android version had this multi-core support in it. It also introduced the multiple document interface, which basically allowed the system to open up different windows for a single app. Nowadays, we take this for granted, and every app can have hundreds of windows, just like on a computer. But back in the days, you could only have one window per app. Another thing it did was, security-wise, it introduced storage encryption, which is a low-level encryption of the user data portion. And this change brings the operating system in line with iOS. So iOS already had that, and Google were playing catch up. This disk encryption layer is on top of the Android secure storage that has been there from the first Android release. Moving on, we got Android 4.0 or Ice Cream Sandwich in 2011. And this version introduced the Android VPN network. So up until this point, if you wanted to build out a VPN or even use a VPN on an Android device, it was pretty hard. Now there was a network that would allow you to do that. Another thing it introduced was Android Beam. And so this was a way for two devices that have Android to communicate with each other in close proximity. So it's a way for devices to communicate. And the final kind of noteworthy change here is the V8 browser engine support. So V8 is the engine behind Chromium or Google Chrome. Up until this point, up until Android 4.0, the browser that were being used in the operating system were using a different kind of engine. So this is pretty big. Moving on, in 2011, we got Android 4.1, or otherwise known as Jelly Bean. Now, Jelly Bean brought a lot of new stuff to the table, starting out with Project Butter, which was an attempt to combat lag and increase the performance, the overall performance in the system. It was actually quite successful. It did that by allowing the CPU and the GPU, the central processing unit, and the graphical processing unit, to run in parallel with each other, which not only increased performance, but it also allowed them to improve the display refresh rate of all of the devices to 60 frames per second. So not only did you get increased performance, but also you had a smoother control coming from the increased frame rate from the display. Another major change which was introduced from this update is that it allowed you to have multiple users on the same mobile device. So every user could have its own instance and own applications and files. And not only that, but the data between the users was secure and in isolation of each other. Another thing, speaking about security, that this update introduced was the application encryption and forward locking built upon the ASEC we were discussing previously. So, what this feature does is it allows apps to have a secure container for their data so that it's encrypted and the data is only used by those applications and no other application. And further down the line, speaking about security once again, this was the first version that introduced the secure Linux environment, which main purpose is to protect the operating system against potential security vulnerabilities. That sounds a little bit vague, but it's actually the backbone of the sandbox environment that Android uses. So as we should know by now, every application and process runs in its own sandbox in Android. And the secure Linux environment is the backbone of this process. Um, so following along in 2012, we got KitKat, and this was a major game changer. So it introduced a lot of stuff here. First of all, this was the first um, Android version that was sponsored by another company. So the name at least was sponsored, KitKat. Originally, it should have been called Key Lime Pie, but then they had a partnership with Hershey's, so they named it KitKat. The first kind of major change that introduced to the Android system was that it now supported Android wearables via Wear OS, so smartwatches, and things like that. Another massive architectural change was the introduction of the Android runtime environment. So this was another type of a runtime environment uh, which eventually would replace Dalvik. In this update, it was introduced only optionally. So if you were an application developer, you could have used it at the time if you wanted to, but it wasn't mandatory. Um, KitKat also had a pet project called Svelte, and its initiative was to enable a smoother experience across all of the devices that were using Android. So Android at the time had a particular problem, and that was with adoption. There were a lot of Android users, but they weren't updating their operating system to the newest version. And they were doing that for several different reasons, but one of them was because they feared that the performance of their device would drop updating to a newer operating system. So if you had an older device, if you update to a newer version of Android, you might have slower performance. And so a lot of people didn't want to update, and Svelte tried to tackle that issue, and it tried to tackle that by you know trying to increase performance on even lower end devices. The cool thing about this project was it also had performance increases for higher end devices. So devices that had more than 1 GB of RAM, they could benefit from a feature called ZRAM or compressed memory, which was already introduced in iOS at the time. So Android again were playing a little bit of catch up, but this allowed them to have improved performance on the high-end devices as well as the lower-end devices. This project was actually very, very successful, and a lot of people started adopting KitKat after its release. Another important feature that was released as part of KitKat was timer coalescing and sensor batching. Basically, these are features related to help improve battery life and power management. So applications would have wake times, what we call wake times. It's when an application uh, goes to sleep after it's not being used. So what these two features did was it synced different applications so that the system would check when they should go to sleep together instead of constantly checking one by one and one by one. Um, and also, it made it be less frequent. Instead of doing it all the time, it did it from time to time, and so it didn't drain as much battery for it to constantly wake up and check for what to kill. So, in a nutshell, that's Android 4.1, 4.4 KitKat. In 2014, Android 5.0 or Lollipop was released. Now, this version of Android made some huge changes. The first one to the Android runtime environment. The old virtual machine named Dalvik was completely replaced by the new Android runtime environment, previously introduced in KitKat. This standard runtime environment had better performance, and it also allowed them to support 64-bit CPUs, which up until that point weren't supported on Android OS. The pet project of this Android release was called Project Volta, and its main aim was to improve battery life and to give developers better battery monitoring. Um, Ironically, this release had a lot of complaints about power management and battery life. Um, some two other notable features that were added were the fingerprint support. At first, it was just an introduction, only system apps could use it, and dual SIM support as well. Following that, in 2015, Android 6.0 Marshmallow was released. Um, the first important feature that it introduced to Android was secure boot and device encryption enabled by default. So both of these features were in Android before this, but now they were made the standard, and every device running Android 6.0 had them enabled by default. So we talked about device encryption before. What Secure Boot does is it checks every application and it only allows the system to boot if it can verify that the files are correct and it trusts them. There was also an app permissions model rework. So prior to Android 6.0, the way Android handled app permissions was upon installation of the application. So you install an app and it will give you a list of permissions it requires from you, and then you will never hear back from it again. Which was a very bad way to approach this problem. Not only because you saw a huge list of permissions you have to enable for each application, and now you're wondering, well, why the hell this camera app want to, spy on me so much? When in reality, most of those permissions would almost never be accessed by the camera app. So they switched to a model which is more similar to the model from iOS at the time, and still is. They were still playing catch up. They switched to a model where app permissions were asked upon launching the apps instead of installation. Some further improvements were made in terms of security by extending the data encryption to external storage as well. Also, there were significant improvements in power management with two new features introduced. One of them being dose mode, which in essence would check when your device would be idle after some periods of time where you haven't used your device. um, the dose mode would kick in, and what it would do is it would restrict the use of the CPU and the networking activities to the applications. The other feature, app idle detection, actually checked if you haven't interacted with an app for a while. So if you have an app in the background which you haven't interacted for a while, um, it would fall under the app idle detection, and so it would restrict its network access in an aim to improve power management. And the final two features are Android for Work, or Android Enterprise, as it is known nowadays. This is a feature that allows you to have a personal profile and a work profile. So it's kind of similar to the multiple user profiles introduced in earlier versions. The difference here is that the work profile can be managed from other people and even remotely. You're not necessarily the one who manages it. And finally, fingerprint reader support was extended to all kinds of applications, including third-party apps. In 2017, Android 7 was introduced. This Android version got its name from the community. Google actually asked the community what they want to call this version, and the popular name among them was Nougat. So that's how this version was named. So Nougat brings a lot of changes to Android once again. The first of them being a change to the Android runtime environment. And so the Android runtime environment changed its Java runtime compiler from the old one, Apache Harmony, to a new one, OpenJDK. And you don't need to understand what that is. I'm adding that for technical details, but essentially it allowed them to future-proof the compiler and also increase performance a little bit. Along with this change, apps no longer needed to recompile after they were updated, and so that not only decreased the file sizes of the applications, but it also decreased the boot times. Some other notable changes were the introduction of the Vulkan 3D rendering API, which was a replacement or more as an alternative to the OpenGL rendering API. So both of these APIs dealt with higher graphical performance, like games and things like that. And finally, verified boot, the authentication framework that ensures devices are running a safe version of Android, essentially when they first boot up, was made the default this Android release. 2017, following that, Android 8.0 or Oreo was released. Uh, in this version, we witnessed the biggest change to the foundation of Android to date. It was a huge initiative called Project Treble, and it served the purpose of tackling a specific problem the people at Android had, and specifically the device manufacturers. So if we look at Project Treble in detail, this is what it did. We first have to understand the problem. So the problem was when a new release of Android hits the market, the process is described on the left. So the Android team releases a new version and then they ship it to the silicon manufacturers. In other words, people who make all of the processors and all of the different chips. Now, these silicon manufacturers make some changes to the Android operating system to fit their own kind of processors, and they make those changes in the hardware abstraction layer, or the HAL. They then pass that version to the device makers, which are the makers of the actual mobile phones who also customize this for each different phone and add their own stuff to the hardware abstraction layer. Once they're done with that, they test it out with phone providers and phone companies, carriers, and then finally it's the end user. Now, the problem with this supply chain and the original way uh, of how Android was doing things is that every time there was an update to the Android architecture or a new Android update was released, the previous vendor implementation or whatever changes that the device makers or the silicon manufacturers made in the hardware abstraction layers had to be reworked and modified so that it works with the newly updated Android version, which was a huge problem and a huge reason why device manufacturers didn't want to update their phones to newer Android versions, or maybe they did want to, but it was taking a very long time for a third party device manufacturer to update their device to a newer version of Android. So Project Treble aimed to fix that issue. And the way it fixed it is it separated the layer even more and it gave the functionality to the device makers to uh, be able to implement the code once, and so that that code can work again and again, even on newly updated Android versions, up to three major versions on top. So this is the new way with Treble. Um, Before this, the vendor had to update their implementation after update. After Treble, they can leave the original vendor implementation and simply update the operating system on top. So there's a real abstraction after Project Treble. And all of those changes happened here in the hardware abstraction layer. So after Project Treble, there were major changes in how the hardware abstraction layer handled things. The other initiative of Android 8.0 was the Android Go initiative. And the Android Go initiative basically supplied a lightweight distribution of the same operating system, in this case Android Oreo, aimed to run better than the normal Android version for uh, lower spec devices, devices that have less than 1 GB of random access memory. And so this initiative aimed to bring those devices up to speed as well, just on a slightly tweaked version of the main operating system. Because those devices also didn't want to update to newer versions because they were afraid that they would suffer a performance hit. So now they also had an alternative. In 2018, we got introduced to Android 9 Pie. This is the last Android version that uses the code names named after desserts, unfortunately. But it's also the first ever Android version that did not require an incremental update for big fixing or anything else. So there's only one Android 9 version. This version had major changes to power management, some of which were the adaptive brightness, which basically checks how bright it is outside and dims your display accordingly to the brightness outside. There are also some privacy features included with the update, such as the fact that apps can no longer perform audio or video recordings unless they run a foreground service. So if they're in the background, they can't do that anymore. And these features were extended in Android 10. So speaking of which, Android 10 was released in 2019, and some of the features it included were foldable phone support. Uh, those are getting popular nowadays. And one of the main initiatives, apart from that, was Project Mainline. And what Project Mainline attempted to do was to allow the core operating system components to be updated without requiring a complete system reboot or system restart. So before this project and before Android 10, whenever there was a slight change in the core operating system components that had to be updated, you had to restart your phone in order for that update to take place, which was fairly annoying because even though in this presentation we're only focusing on the major releases, there are a lot of small updates being pushed between them, which all required an update to the operating system. So it required you to restart your phone. So with Project Mainline, it attempts to update some of these components without needing to reboot. It directly updates them via the Google Play Store, similar to how typical user applications are updated. Um, Another thing it changed is some of the privacy policies. So again, specifically to background applications, if a application is running in the background, it cannot have access to the camera, microphone, um, and the sensors are disabled as well for better privacy protection. However, this had the funny downside that a lot of anti-theft software that relied upon these features were effectively disabled. In 2020, Android 11 was released, and this is the current Android version at the time of recording this presentation. Um, it mainly introduced new permission controls, such as one-time permissions for apps, so that you can grant a permission only once for an app, and then next time you open it, you have to grant that permission again. Also, it introduced permissions auto resets, so that an app's permissions aren't granted forever, but they can be reset after a period of time. The next version of Android is Android 12, and it's scheduled to be released soon, perhaps towards the end of this year, 2020 again. It's supposed to have more performance improvements, and it's supposed to add the Android runtime environment to be updatable with the other Core OS components, along with Project Mainline. And that's it. Thank you for joining me on this journey into the Android architecture and how it has evolved throughout the years. We also understood what's the common thing between how, Dalvik, Art, and Cupcakes. So I hope you enjoyed that.